Hi everyone, so this is a review for Chapter 10 Revision Quiz, Set 3. So we have 29 responses, not a lot, I wish much more. So we'll be discussing question 4, 5, 9, 12, 16, 17, and 20. Basically all the questions that has more than 10 people who don't know how to do it. Okay, so let's proceed with question 4. Question 4 provides you two equations, and these are equations that are related to the standing wave on a stretched string. Okay, so then they ask for, can you observe standing waves with a wavelength of 3 meter on a string with a length of 2 meter? So they are asking, if I have a 2 meter length string, can I make a standing wave which have a wavelength of 3 meter on it? Is it possible? Okay, they are very specific. They ask about standing wave. Okay, then they ask if it's possible, then which harmonic is it in? Okay, so this is the question we are going to solve. Well, actually, when they give you, if they give you the equation already, I think you just make use of the equation being given. So they give you n lambda over 2 is equals to the length of the string. Well, this is the relationship between the length of the string and the wavelength for a stretched string. So we know our L will be equals to 2 meter, and our wavelength will be 3 meter. So if we substitute these two things inside, we get 2, 3 over 2, n. Okay, then this one will be n, 1 over 5, 2, and 2 over 1 over 5. 1 over 5 is basically 3 over 2. Then you end up with 4 over 3. Okay, which is about 4 over 3 is 1.33333 if I'm not mistaken. Yes, 1.33333. Well, if you say, if you are being just mathematically involved, then you say, oh, n equals to 1.33, then yeah, it's not n, it's not 1.5, but it's 1.33, so it must be some other n. So you might be just being, yeah, you think very fast and you put this as your answer. But no, incorrect. Why is it incorrect? Because when we talk about this equation, n can only be integer ranging from 1, 2, 3, 4, and other integers. Integers means by they cannot have decimal places. It must be a whole number. 1, 2, 3, 4, 5. This is integer. So n actually means by which harmonic is it in. So you can't have 1.5 harmonic. You can't have your first and a half harmonic. There's no such thing. There's no second and a half harmonic. Okay, harmonic proceeds in multiples. Okay, means that 1, then you multiply becomes 2. Okay, then the next, it's a what do you call it, arithmetic progression with a leap of 1. Okay, so it must be an integer. Well, you can graphically prove why can it only be an integer. Okay, let's say over here, let's say you want to build a 1.33n standing wave. So if this is your string here, if this is my string, oops, what am I doing? If this is the string and I want to build a 1.33 mode standing wave, 1.33 of half of the wavelength will be something like this. You will have 1 half wavelength, this is 1 half lambda. Then you add on another 0.33 of this. 0.33 of this is about something around here. So add on another this much. So this is the standing wave that you want to produce. If you now put it into the wave, then you will see something like this. Now, why this thing is illogical? Why this thing can't happen? Well, your string is fixed at 2n. When you're creating a standing wave, the string must be fixed at 2n. So if this one is a node, this one is also a node, because both of these two ends cannot move. But now you're showing that you have displacement. You're showing that you have displacement at one end. If you are building a node, if you are building a normal mode with n equals to 1.33, normal mode means harmonic. You're building a 1.33 harmonic. No, because you have displacement at the end. You have displacement at a place which is supposed to be a node, and this is illogical. That's why the answer should actually be no. You can't create a harmonic of wavelength equals to 3 on the length of string which is 2 meter. A 2 meter string can't contain a standing wave of wavelength 3 meter. Okay, so that's all for question 4. Let's move on to the next question. Question 5. Question 5 says you have a string which is vibrating with a fundamental frequency of 220 Hz. Fundamental frequency. Fundamental frequency means what? The lowest possible frequency of standing wave that can be produced in the medium. In this case, our medium is the string. Okay, so now they ask, besides 220 Hz, which of the following are resonant frequencies which you might also have? So is there any other possible resonant frequency? So if I look into the comment section in the Google form, many of you is asking, what is resonant frequency? So can you explain resonant frequency? Well, resonant frequency are all the frequency of the harmonics that you have. Okay, let's say this is your string, maybe. Okay, your string is this string over here. Then based on this string, you can say this string has a length of L. Okay, then you also say this L will be equals to n of half of lambda. Okay, this is the multiple of half of wavelength that can contain within this string. This n represents which harmonic you are in. And after that, you can use V equals to F lambda, and you combine them, and you can form L is equals to n V over 2F. Then if you shift around, then F will become, okay, now this is difficult, my brain cannot process, NV over 2L. Okay, so this is the frequency of the standing wave that can be produced on this stretch string, and usually I'll just put it like this so it's easier to see. Okay, as you can see, this here will represent the fundamental or the first harmonic frequency. Then any of this later will be another harmonic over here. So if this is our fundamental, our Fn here represent the resonant frequency at the nth harmonic. Okay, so usually you call it frequency, right? You say this is the frequency of the nth harmonic. Well, this frequency of harmonics, the frequency of the harmonics are actually called resonant frequencies as well. That's because, okay, let's say, let's just use this example. Your fundamental frequency is 220, right? It's 220 hertz. Now this, if this is f1, then your next f2 will actually be just times n, right? If you substitute n equals to 2, then the second harmonic will be 440 hertz. Wake. 440 hertz. Well, actually, have you ever wondered what happens to all the frequency in between? How about all the frequency in between? Well, the thing is, all the frequency in between can't produce standing wave because it cannot achieve resonance in the string. Okay, so just now I say this is illogical, you cannot make it because you have some fixed condition being imposed in the system. This is a static condition, means like your system is born this way. Okay, your system has some limitation. The limitation is it cannot move at the two ends. So if this is the restriction you have for this system, there are only a few frequency that can be constructed very effectively on this string. Because you have this restriction here, it cannot produce any frequency of standing wave so easily. Okay, only those proper wavelength, proper frequency, only you by creating this kind of standing wave you can achieve resonance. Let me susun my ayat a bit. Okay, if you go back to this example, let's say you want to create a 240 hertz, let's say want to create a 240 hertz wave, standing wave, you can't create it. Why? Because you have restrictions of your system here. Your system is being restricted at the two ends already. Under this restriction, 240 hertz is not a frequency that can cause oscillation very smoothly on the string, whereas 220 hertz, the string will oscillate very comfortably. If it's 440 hertz, the string can also oscillate very comfortably because it respects the restriction at the two ends. We have restriction at the two ends, and these two frequencies respect the end condition here. So we can achieve maximum, we can achieve a very good pattern of standing wave. Whereas any frequency in between, right, because it cannot be fit into this end condition here, you cannot produce resonance. You cannot produce resonance, so you cannot see a very consistent pattern of standing wave. Okay, if you still cannot get what I mean, right, I suggest you to watch Walter Lewin's lecture. Okay, it's in your GC, is one of your tasks last time, the 50 minutes or 1 hour lecture. I think the name is The Sound of Music. Okay, over there you will see Professor Walter Lewin. He will conduct an experiment, a demo, okay, where he tried to create standing wave on a red color string. And as you can see, right, when he is oscillating his hands, right, at certain frequency you can see a very clear standing wave. Then when he increases his frequency, then you cannot see any proper standing wave in the string because resonance can't be achieved. He is moving from here to here. So in between, in this area over here, he can't observe standing wave because all these frequency in between cannot achieve resonance. You can't observe standing wave in the middle. Until it reaches the appropriate second harmonic, only you see another standing wave come out. Okay, so this fundamental frequency represents the first frequency that you can find resonance in the string. Then second harmonic represents the second frequency where you can find resonance in the string. So first harmonic, second harmonic. If you don't understand me, go watch the lecture. The demo, I think, explain it really clearly. So as I said here, 220, if it's a fundamental, then the next one will be 440. You cannot go lower than 220 because that's the fundamental. Fundamental is the lowest, so you cannot go lower than 220. 330, it's somewhere in between. If it's somewhere in between, you cannot achieve it. No. So the answer is 440 only. That's why the answer will be number 3, not 1 and 2. So that's it for question 5. Let's move on to the next question. Okay, question 9, the next question. A string which is fixed at both ends, so we can call it a stretched string, on an instrument placed at 440 Hz. A here means by a specific note basically. Okay, place a note which has a frequency of 440 Hz. When plucked, okay, it's just like a guitar. If you pluck a certain string, then you get an A note. I'm not sure which string, okay. If you press the string hard to the fret, just like guitar, the hand, the place where you press different keys, press different notes, that place is the fret. So they say it press the string hard at 1/3 of the way along the string. So you press at the place where you will split the string into 1/3 of the string and 2/3 of the string. You press at that position, then you pluck the longer side. Pluck the longer side means by you pluck the 2/3 of the length that side. Okay, then what frequency will you likely to hear? So they ask for the frequency. With that, let's try to figure this out. Okay, so let's draw the string first. Okay, so this is my string. Okay, for my string, I say it's fixed at both ends. No, not I said. The question says it's fixed at both ends, so both sides are notes actually. Then it says it creates a frequency which is 440 Hz when plucked. Well, if you are plucking a guitar string, right, let's say, what kind of frequency you find is actually a fundamental frequency plus a few higher harmonics. Okay, let's assume this 440 Hz here is the fundamental. We assume only. It doesn't have to be true. We assume it's the fundamental. Okay, so that's another side here, which is the other opposite. Something like that. Sorry for the bad drawing. So after that, you are asked to press the string hard to the fret. So you press it until the string touch the fret. At where? At 1/3 of the way along the string. 1/3 along the way, so we can think of is we split it into 3, somewhere around here. So we press here. We press very hard here. Press to the fret. Okay, then after that, we pluck the longer side. Means why we want to pluck this side of the string. So maybe we can say we pluck here. Okay, so if you pluck here, then he asks what is the frequency that you will likely hear. So in that case, we can sort of roughly imagine that the standing wave now will look something like this, and it will look something like this. Okay, so this is the new standing wave that we will produce when we shorten the length of the string. Well, this is how a guitar works actually. You press on the string, you are limiting the wave to be standing inside this place, the end of the string, and the place where you press. Then the string outside will not be involved. So you are temporarily making the string shorter actually when you press on the fret. So let's find the new frequency. Okay, from here we can see that this is half of the wavelength, so the length is equals to half of the wavelength. Okay, we just assume it to be like this. Okay, it's not necessarily true. So if we combine it, if v equals f lambda, well, the reason why you see me cannot give you the exact formula every time is because I never really go memorize the formula. I usually derive everything on the spot. So this is v over 2f. Then if you switch things around, then it will be v over 2l. Okay, so this is the fundamental frequency. I'm doing it for fundamental frequency here. Okay, so if we look at this case, we know that this fundamental frequency is 440 hertz. Okay, now we shorten the string. We shorten the string means by the new length is 2/3 of the old length. Why? Because we press at 1/3 of the place. We can think of splitting the string into 3 parts, then we press on the first part. So we limit the standing wave to 2 out of 3 of the string. So 2 out of 3 of the string. So this is the temporary new length. With that said, how will our fundamental frequency change? Our new fundamental frequency will be equals to v prime over 2l prime. Okay, let's say everything changed to the new condition. So let's determine what's the new v and the new l. Well, the new v, okay, this one I need to ask you again. If I say v must depends. Okay, this is the third or fourth time I'm saying this. You should continue my sentence now. Depends on only on the medium. Okay, depends only on the medium. Means by for a stretched string, right? This is the thing that determine the wave speed on the wave. Only these two things determines what's the wave speed. These two things are properties of the medium. They are not properties of the wave. So these two things decides on the wave speed. Then you use this wave speed, you put it inside the v equals f lambda. So actually this is constant if you don't change the t or mu. Okay, it depends only on the medium. So are we changing the t? No, we are not making the string tighter, we are not making the string looser. Are we changing the mu? Definitely not. We are not changing the string. Only by changing the string, the density, the thickness, the diameter of the string, only you are able to change the mass per unit length of the string itself. So if you are not changing both of these, then the wave speed should be constant. If wave speed is constant, we can reach the conclusion that new v will be equals to the old v. So we can just write this as v over 2. Now the new l, we just substitute 2 over 3l from up there. So now if you flip things around, you will see that this is equal to 3 over 2 of v over 2l again. And now if you see here, v over 2l is just the fundamental frequency previously. So we can say it's 3 over 2 of the previous fundamental frequency, which is 440 Hertz. With that said, we are able to find the answer, which is just this one. Okay, so this will be our answer. So just now I say I assume this to be a fundamental tone, right? So this is the fundamental first harmonic. Well, is it necessary to assume this? Well, actually no. If you start with a general one, which is L equals to N lambda over 2, and we have this, then if you substitute things inside, you will still get N inside, then this one will not have standing wave, so the frequency is N times of 440. Okay, if it's N times of 440, then you use the new equation, you remove the standing wave fundamental, then you will still end up with 3 over 2 times the frequency of standing wave. Then you just use this frequency of standing wave to be equals to N440. So you can also get the same answer at the end as well. Okay, nothing to worry about. So you still get the same answer if you generalize it using the general formula. Okay, so that's all for question 9. Oh, before you move on, 3 over 2 times 440, 3 over 2 is 1.5. It is 1.5 means by the frequency gets higher. Higher frequency means higher pitch actually. That's why if you are playing a guitar string, if you press nearer to the place where you pluck, then you have shorter and shorter effective length, your pitch will go higher and higher. Go watch a guitar player if you're not sure what am I talking about. Okay, so now we officially move on to the next question. Make this larger. Okay, so question 12. Question 12 says you have the air in an open pipe. So this is an open pipe. If you hear the word open pipe, get a bit sensitive. Remember, it'll be antinote and antinote, because there's plenty of space to vibrate here, plenty of space to vibrate here. So it will displace to its maximum. So antinote, antinote. It's vibrating with a second harmonic. Okay, so you know the N is equals to 2. Then a small speck of dust is located half of the way down the pipe. Okay, so I think the diagram here is labeled clearly. This blue dot here represent our dust, and it's halfway down the pipe. It's halfway. So L is L over, the distance is L over 2. So what will the dust do? What does the dust do? So you're asking whether the dust will move or whether it will not move. If it's moving, how will it move? So that's the question that we need to deal with for this question. Okay, so it's an open pipe. Okay, like I said, I don't really recall a lot of formula usually. Oops. So let's draw everything out. Okay, so this is my open pipe. Okay, open pipe means by the two ends must be open. So I have to clear the end. So this is my open pipe, and I'm creating a second harmonic inside. Okay, if you cannot immediately imagine a harmonic, you work like this. You know that both sides are antinote, because open pipe means by a lot of place to vibrate here, a lot of place to vibrate here. This is outside world already. You have plenty of place for the particle to vibrate, plenty of place to vibrate. You vibrate at its maximum. So this is an antinote. You know A and A cannot be side by side, therefore it must be splitted in between with an N. So this will become the fundamental frequency, or the first harmonic. Now they are asking for the second harmonic. They are not asking for the first harmonic. So what you need to do is you need to figure out what's the configuration for the next harmonic. So for the next harmonic, you know that the middle will not be that simple. Okay, so before this, if there is an n, so now I would like to add on another a, or we want to add on one more n inside. So if we have one more n inside, now we have to figure things out, how to make the n not side by side and how to make the a not side by side. Okay, if you move from one harmonic to the second harmonic, you increase the number of notes inside. So when you move to the second harmonic, you add on another note. So now if you add on another note, you might think this is the answer, but no, because n and n are side by side right now. So we need to figure something out so that we can make this thing logic. Okay, this is how I think about every harmonic actually. So to make this logic, I need to add something in between the n and the n to make everything not side by side. So now a is not side by side, the n is also not side by side. So the last thing I need to do is clear things up a little bit to make things nicer. So the n should be around here, the n should be around here. Now done. This is the second harmonic. Okay, just by pure logic and knowing how a pipe looks like, you can determine the harmonics that you need to draw. So antinote means by vibrating at its maximum displacement. Note means by not moving at all. So this is the equilibrium position. Okay, if you're interested to see an equilibrium, let me draw an equilibrium for you. Maximum, equilibrium, maximum. Okay, so with that, we can draw the second harmonic to be something like this. Again, I apologize for my bad drawing. Something like this. And then the next one usually is a dotted line. Something like this. So this will represent the second harmonic. Okay, I'll call this the first. Fundamental is the first harmonic. So this is the standing wave pattern that is produced in our open pipe right now. Then they are asking for this particle over here. This blue dot over here, whether it will sit still at the center, or it will wiggle up and down, or it will wiggle back and forth. Wiggles up and down means by the particle will move up and down like this. Wiggle back and forth means by it will wiggle like this cursor over here. Sit still means by it will sit still over here. So if you are being very fast, you don't think carefully about the theory, you might see that, oh, this here means by its displacement is maximum. If displacement is maximum, then you will feel like this speck of dust over here will be now over here. So you think it wiggles up and down. So you might straight away go put your answer as wiggles up and down. But that will be wrong, because you need to recall, if you have you have standing wave being produced in the pipe. Inside there, it's sound wave reflected, incident sound wave and reflected sound wave combined together. So actually, it's a longitudinal wave that we are talking about. It's not a transverse wave. So if it's transverse wave, if it's longitudinal wave, means by the particle should actually wiggles back and forth instead of up and down. Because longitudinal wave means by your wave, incident wave is going this way, your reflected wave is going this way. Longitudinal wave says that the vibration of the particle is parallel to the propagation of the wave. Means by your particle should also vibrate in parallelly to the propagation of the wave. Okay, so it should be back and forth. You should see your particles wiggles back and forth. So in that case, your correct answer should be wiggles back and forth. That should be your answer. Okay, if you want to, then you might be asking, then why do we draw this kind of graph? This kind of graph doesn't look like a longitudinal wave at all. This looks like a transverse wave. Well, you are partially right, The thing is, we always deal with transverse wave, so we never really draw properly how a longitudinal wave looks like. So let me draw for you what does this mean. Okay, let's pick a few points. Let me pick this point, 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 and this point. Then let me draw dotted line downwards. Okay, we will try to understand what does this graph means in terms of or for a longitudinal wave. For transverse wave, it's easy to imagine. If you see the displacement is maximum downwards, then that is the place of the particle. But that's if it's a transverse wave. Now we are dealing with longitudinal wave. What does it mean? Okay, let's go focus on the node first. If you see node, then you see that the displacement is equal to 0. This is the equilibrium position. So you see the line pass through the equilibrium position at this point. So at this point, the particle remains at its equilibrium position. What does it mean? Our particle will remain at its equilibrium position. This position here represents the equilibrium for the particle at this position. If it's not at its equilibrium, it will move either this way or it will move either this way. That's the meaning of this graph actually. Let's continue. We have another node. So equilibrium position. So this particle here will also be at its equilibrium. Now let's move towards the antinode. The antinode shows here I have positive maximum displacement. Positive maximum displacement means by I'm moving in the positive direction and I'm now at my maximum. So I say it's oscillating back and forth, right? So the positive is towards this direction and it is now at its maximum. So it's somewhere around here. Okay, the particle moved that much. Okay, then look at this one. This one is a negative maximum. Negative maximum means like this is my equilibrium. I move to the negative direction for maximum. So it means like it's somewhere around here. The particle moved that much. Okay, whereas for the antinode over here, it's to the right and it's maximum. So it's somewhere around here and I move that much. Okay, so that's the antinode. Then let's look at the points between. Well, it's not the maximum, but it's moving to the positive direction. Not the maximum, but somewhere in the positive direction. So equilibrium is here. So I move somewhere to the positive direction, but not that much. So somewhere around here. So I move about that much. Okay, then for this one, it's moving to the negative direction. Not that much. Not that much as this antinode over here. So what do? This is the equilibrium point. We move to the negative side, but not that much. So it will be something like this. That much only. Okay. This one also moving to the negative because it's below the equilibrium point. Negative, and it's not that much. So the particle here, negative, not that much. Somewhere around here. This one will not be moving, just like what we say. This one is moving to the positive, but not that much. Positive, not that much. Okay, so that will be how the particle looks like in the standing wave. So let me remove the arrow so you can see things clearly. Well, do you see some pattern? You can see that this section here is experiencing a compression. Then this section here is having an I think this is an expansion, compression and rarefaction. Okay, so this is the situation that might occur if you are seeing a second harmonic. So this is how a longitudinal wave is produced in an open pipe actually. So if you change it, if you change from this side, then you oscillate the standing wave pattern to another side, then you will probably see this side having rarefaction, this side having compression. So it's a switch between compression, rarefaction, compression, rarefaction. It's on rarefaction, compression, rarefaction, compression. So that's the idea of what does this line, this standing wave sinusoidal curve here means. It means how much you are being displaced to the left or to the right. Okay, too much explanation. Yes, that's all for question 12. The answer will be wiggle back and forth. Okay, so that's all for question 12. Let's move on to the next question. Okay, you are standing stationary. Question 16. You are standing stationary and you see an ambulance approaching you. Okay, so you can think of, later I will draw. Okay, and it's approaching you with constant speed while keeping its siren on. So it's ee-oh, ee-oh, then it's approaching you with constant speed. Important, constant speed. After the ambulance has passed you, after passing you, then you will continue to listen and they ask for the pitch. Okay, so this question 16 here is a continuation of question 15, but most of you only request for 16. The ambulance is coming towards you. This is you over here. Because having a siren here, then this is actually a source, and you as a person who listen will be the observer. Okay, before this, the ambulance is moving towards you. Then after it moves past you, you continue to listen. Then they ask for the pitch. Ask for the pitch right now. Okay, so that's what we are going to figure out. What's the pitch right now? So actually, I'll just start by reviewing the answer. The answer will be it stays fixed, but it's lower than where it began before passing you. Okay, to know that, right, you have to look back to the formula. Okay, the formula here is f prime equals to something of f. Okay, for now your observer is stationary, right? So later when you do the v over v thing, up here will be for observer, down here will be something for source. Okay, if your observer is stationary, means by you don't need to change anything up here. You keep the v, that's all. But sound source, is the sound source moving? Yes. So you have to consider the sound source moving. Then you have to introduce the component called speed of the sound source. So that's your equation, but you need to determine whether it's a plus or a minus. Okay, so now let's look at the situation when it's approaching you. If it's approaching you, then you definitely hear a higher frequency wave because it's approaching you. If you can recall any ambulance, if it's approaching you with a higher pitch. So you know the f prime approach, this is approach. When it's approaching you, the f prime will be larger than f. So when you construct your equation right now, you know you need to have v and v of sound source times f. If you want the f prime to be larger than f, then this must be greater than 1. If this must be greater than 1, then above must be greater than below. So above greater than below means by you need something smaller down here. So if you want something smaller down here, you should put a minus sign. So that's your Doppler wave equation when the ambulance is approaching you. But if it's moving away, If it's moving away, then you hear a lower pitch sound actually. You hear a lower pitch sound. So what is the formula for the pitch? Before that we write F prime will be lower compared to the sound produced, the frequency produced by the source. So how do you calculate it? It will be the similar equation. You have V and your V of the sound source. The V here represents speed of sound. So what symbol to put here? If you want F prime to be smaller than F, it means by this thing must be smaller than 1. Smaller than 1, only you are able to get a smaller value here. So to be smaller than 1 means by the below must be larger than the above. So we want to make the below larger. How to make it larger? By putting a plus sign in between. That will make things larger. So this will be our equation here when the ambulance is moving away. So now you see here, it mentions here that the ambulance is approaching you with constant speed. Then it passes you also constant speed. We assume the whole journey is constant speed. So now what will happen? So as time passes, your this thing is always 343. So this is a constant. As time passes, the speed of sound never change. This one also never change. Our ambulance speed also never change because it's moving with constant velocity. So all this while, everything here is constant as time passes. Our sound of the siren, we never really change the siren. So the frequency of the sound produced by the siren is also constant. So what does it mean? The new frequency that is produced will also be constant. It's higher than F, higher than the frequency produced by the siren, but it's still constant. It's still constant even though it's higher. That's why the pitch that you hear will stay fixed actually. Because you hear a constant, it's not like you hear that kind of sound. It's not like it's increasing in pitch, or it's not like it decreases in pitch. It's a constant higher pitch, something like this. Okay, constant higher pitch. So if it's moving away, now it's moving away, you know that, okay, by the same idea, all these things here will be constant, 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 constant. So this frequency heard by the observer will also be constant, but this time it's lower than F. So lower than F means by if F is then the sound that you hear will be it's a very bad representation, but it's lower than the frequency of the sound produced, but it still remains constant. So it stays fixed, but it's lower than before it passed you. Means by it's lower than this frequency here, lower than this frequency here. Okay, if you don't want to make it confused, let's call this 1 and 2. So the new frequency when it just passed by will be lower than the first one. Actually, in fact, it's something like this. Lower than the frequency of the sound produced, then yeah, something like this. When it's approaching you, it's the highest frequency, higher than the frequency of the sound produced. When it passes by you, it's lower than the frequency of the sound produced, and it's lower than the frequency of the sound when it's approaching you. Okay, so that's the relationship. That's why if you look back into the lecture note, you will see something like this. Frequency, the position, okay, hertz. Then you will see a graph that looks something like this. When it's approaching you, it has a higher frequency. Then when it just passes by you, it will experience a drop. Then when it's moving past you, it will have a lower frequency. So this center here will be F, whereas this one here will be your F1. Okay, f1 prime, whereas this one will be your f2 prime. This is approach, this is moving away. Okay, that means by you are standing here. Okay, so that's the idea behind this graph. Okay, so that's all for question 16. The answer is stay fixed but lower than where it began before passing you. So that's all for question 16. Let's move on to question 17. Question 17 says you have a child and it's swinging on the swing towards a person which is blowing a whistle. So this is a swinging, or it's poorly drawn, but a child is swinging from A to B to C to B to A to B to C to B to A, something like this. It's swinging. So at which position will the pitch sound highest to the child? So remember, it's Doppler effect here because you are changing pitch. The Doppler effect here says that it's something like this. Then you have V and V here. So what should you change? Above or below? What should you change? The sound source right now, the person which is whistling, it's standing here only. So the sound source does not change. So if the sound source does not move, then you don't need to change the bottom. Okay, the denominator you don't need to change. So what you need to change is only the part of the observer. Observer is up here. Because the observer is moving, you have observer speed. So you have V not V not V of the observer, speed of the observer here. So now you have to decide whether it's plus minus. Okay, so if the person is moving from A to B, then it's moving toward the observer. Then if the child is moving from B to C, it's also moving towards the observer. But here it's speeding up, but from B to C it's slowing down, then it will stop at C. Okay, it is at rest here, it is also at rest at C, then only you can change direction and go back to B. Okay, so if it's speeding up towards B and slowing down and moving away from B, it means by B is having the maximum speed. 0, maximum, 0 speed. Okay, if your maximum is here, means by your V observer will be the largest at B. If V observer is the largest at B, it means by if your equation here, pardon me for a while, if your equation here it's V plus V observer, then at B you have the highest V observer, then this will be the largest right now, then your F prime will be the largest when it's at B. Okay, when it reaches C, okay, let's just write it out. Okay, let's don't try to save time. At position A, it's at rest, right? At rest, if it's at rest means by your F prime will be equals to V plus 0 over V. So your F prime will be just equals to F. So same frequency as the sound produced by the whistle. Okay. Then now it is speeding up while moving towards B. Speeding up while moving towards B. So from A towards B, this thing is continue to be your equation because it's moving toward. That's why you hear a higher frequency. Moving towards higher frequency. So if you want higher frequency compared to F, means you have to plus. Only up there will be bigger, only this will be bigger. Okay. So this will be V plus V naught, not V naught, V observer times F. So when it's moving from A to B, this is increasing. The V observer is constantly slowly increasing. Then when you reach B, let's too many color pen right now. We are moving to B, then you have reached your V observer maximum over V. So at this point, this will be the highest frequency heard by the child. So technically you can finish the discussion here, then your answer is B. Okay, why is it B? Because if you continue to look at from B to C, you see that this equation here will still be moving toward, it's still moving toward. If you look at this equation here, this V observer here is decreasing. If V observer is decreasing here, means by this will be decreasing as well. At this point is increasing, later is decreasing. Okay, so when you reach point C, then it will come back to F prime equals to V plus, let me move out a little bit, V plus 0 over V. Then at this point, your frequency heard by the child will be same as the frequency heard by produced by the whistle. So you can see it's same frequency as the whistle, with the sound produced by whistle slowly increasing, reach the maximum frequency, decrease, and back towards the original frequency produced by the sound. So it's like no. I cannot make a sound. So means like original, increase, maximum, decrease, back to original. So that's why the highest pitch is here. Now if I change the question to ask at which position will the pitch sound the lowest to the child, let's think for a while, pause the video, think what is the answer. Okay, the answer will still be B. Why? Because when we are asking for the lowest pitch sound, right? So when it's moving away, then the pitch will be lower than the pitch produced by the whistle. So it will decrease in terms of frequency, but because you are now decrease in frequency, but because now you are slowing down when you move up here, the V of the observer will be slower here. We can imagine. No. For this case, it is speeding up here and slow down here. So here will be V observer maximum again. Okay, then here will be 0, here will be 0. In that case, if you are using the equation for moving away, the equation will be F prime equals to V minus V observer divided by V times F. So when this thing achieves maximum, then this up here will become the smallest. This one achieve maximum, this will become the smallest. And if this is the smallest, F prime will be the smallest. That's why when it reach here, it will decrease in frequency, decrease, lowest frequency, then it will increase. Why is it increasing when it go back up here? Because this V naught here is getting smaller and smaller, then this thing up here will become bigger and bigger. If this up here is getting bigger and bigger, then this one will get bigger and bigger as well. So it's increasing when you go up here. Decrease in frequency, reach lowest frequency, increase in frequency, get higher and higher frequency until reach the frequency produced by the whistle itself. So original, lowest, original. Okay, that's the other way around. So at point B, you hear the highest pitch and you hear the lowest pitch. Both of them will happen at B. a very interesting thing actually. Okay, so that's it for question 17. Let's move on to the next question. Okay, this is the last question, question 20. Question 20 says here that the above picture represents wave fronts of a sound wave emitted from some sources. Which source is moving at the speed of sound? Okay, this question I'm not sure whether it's in your syllabus or not. That's why I just asked it. Okay, so it's quite easy actually. If you see this case, then you know that the sound source is stationary. Then you see these three cases here, you can see that it is having a pattern of moving to the right. Okay, so these are patterns of Doppler effect. Now the question to ask is which one is traveling at the speed of sound? Okay, so it's something like this. If you have a source here, okay, then your source is producing a sound wave. If it's stationary, then if it's stationary by the amount of time which is equals to period, the distance traveled by your sound wave will be equals to velocity times period, which if you do v equals to lambda over t, then vt is actually equals to lambda. So the distance traveled will be actually equals to lambda. So as time passes, as a one period passes, this thing will move by a distance of lambda. Then this wavefront here will move by a distance of lambda, whereas this thing doesn't move. Okay, so now if this thing happens to have this source here, let's say the speed of the source is not 0 anymore. Let's say this speed of the source is moving to the right. Then even though this wavefront here moved by a distance of lambda, but this source here will get closer to the wavefront before emitting the next wave. That's why the wavelength gets smaller. Because even though the wave travels by a distance of lambda, but at the same time the sound source is actually also moving at the same time. The sound source is moving by a distance of v of the sound source times the period. V sound source. Okay, so it's moving. So if both things are moving to the same direction, and this one, then it means by the wavelength will be smaller compared to when this thing is stationary. Now if it's moving with the speed of sound, okay, let me remove all this. If it's moved, if it's moving with the speed of sound, the moment, let's just focus on one, let's remove the other one. How much, let's say, okay, now this is a bit difficult to explain. Okay, you have your sound source here, then this is at time equals to 0, you admit your first wavefront over here. So the wavefront was here, created over here. Then a certain time later, at time equals to period, if this is moving, if the source is moving at the speed of sound, the source is here. Okay, at time equals to t, your source remains here and your source is moving. But let's look at the wavefront here. Your wavefront, when time is equals to lambda, it will move by a distance of this much. How much is the distance between here and here? This can be found out by taking the speed of sound. Speed of sound, we don't have a subscript. Speed of sound times the period. Okay, then you know that the wavefront here travel by a distance of this much. But how about the sound source? If the sound source is also moving at speed of sound, how much will the sound source move? The sound source will also move towards this direction for a distance of v sound source times t. And since we know Vs, if it's equals to the speed of sound, then it will be equals to Vt. So it means by the sound source also move towards this direction, move until it reach here actually. Sound source move from here towards here. So you can see that the wavefront is actually sticking to the sound source. Then now at this position, it produced the next wavefront. The next wavefront will be here as well. So together they will move away. Then if they move away, the sound source and the wavefront stick together. That's why this will be the correct answer, because the sound source will always stick together to the wavefront. So everything will stick together. That's why you see all the wavefronts stick together like this. Okay, so this is a situation where the source is moving at the speed of sound. This is stationary. This is moving at the speed of sound. This one you see it didn't really stick very well. If it stick really well, everything should be on the same line. This one doesn't really stick very well. This one means by the speed of the sound is less speed of the sound source. Okay, the speed of the source is less than the speed of sound. If this one, you can see the small circle goes over the larger circle. Okay, it goes out of the larger circle, means by the sound source is moving faster, means by as time equals to t pass, the sound source is here, so the new wavefront is out from the old wavefront. The new wavefront is out of the old wavefront. The old wavefront is here. So this one means by the speed of the sound source is actually greater than the speed of sound. We call this breaking the sound barrier. Okay, and we can also call this supersonic. Okay, so that's the meaning of supersonic. You're breaking the sound barrier. Usually you can see this in Mach. You can see this with jet that are having a very high speed, greater than the speed of sound. Then you see you hear a sound, that kind of sound. That's when the sound barrier hits you. Okay, out of your syllabus, if you're interested, go type YouTube supersonic, or you can type breaking the sound barrier. Then you see a lot of videos regard seeing this kind of phenomena happen. Okay, so the answer will be this. When it's moving at the speed of sound, it should be the wavefront. Okay, so that's all for question 20. We have discussed 7 questions: question 20, question 17, question 16, question 12, question 9, question 5, and question 4. So that's all for chapter 10 revision quiz set 3. Thank you very much.